a really bad idea today. Then we're going to postpone the deadline by a week. And maybe, Alex, Shivam, you can help me to send a message on eClass in this respect so that people who are not able to join today also have a chance. I'm like, we had plenty of time to discuss. So if anyone would have a really good reason to protest, they can still, but like, let's not postpone this indefinitely. And then I'm happy to give you guys one more week. Okay. Good. Alex, Shivam, can you do that? Okay. All right, let's start. So today we're going to talk about local planning or online planning. I'm going back and forth between these names. These names are not quite standard yet, so I'm also struggling with that, but hopefully that one day they'll be standard. So last time we already started to discuss this, that we somehow want to free ourselves from the requirement that we have to compute a policy upfront, which would mean that you need to be able to say, without consulting the model, the environment, again, what action to take at any state of interest. And obviously just writing down such a policy for an arbitrary MDP is going to require memory or space that's proportional to the number of states. Since there are too many states in a word, we can't do this. And maybe a better approach is to relax these requirements. And so that's where local planning and online planning come in. So there is this why and what, like how do we define this? And for this, maybe a little figure could be useful, where we have the usually interaction diagram. So we have this controller or agent, and we have the word, which is in this class just big MDP. And the agent sends actions and receives states. And upon receiving some state, maybe it receives some reward as well. It has to compute the next action. So this is the online loop that eventually we want our agents to participate in. So we're thinking about programs to do this, like to perform well in a loop like this. And here the thinking goes that maybe the agent somehow magically has a little copy of the word. So that's an identical copy of the word. How lucky the agent is to have this copy. And if the agent has this, why can't it have just a little program that, just consults this word in its head, it can send actions to it, and maybe it has some extra interface, so it can also say that, hey, word, your state should be this. This is the action. What is the next state? And what is the underlying reward? And then this is going to be the planner. So the planner is going to receive, this current state, and then goes into this loop, this planning loop, of repeating this, like, give me some information about yourself, give me. And eventually, the planner can decide that, okay, I have enough information, and the action that I want to take is just this, right? So if I zoom in, then here you have this word, and we're going to call this the simulator of the word, because it's a simulated word. And then here we're going to have the planner, and the planner is getting a state and then sends queries in the forms of state action pairs to the simulator that faithfully simulates transitions. And the simulator responds with next states and maybe the immediate reward underlying the given state action pair. Okay, so this is what's in the head of the agent, and the agent runs all these queries in a loop. So this happens many times. You have this nice loop, and at the end, the agent needs to come up with an action. So if these responses are stochastic as they should be, right? So that the simulator is a faithful simulation of the word means that if the word was stochastic, then this next state is sampled from the underlying distribution of next states. Then everything is stochastic and the outcome of this computation is stochastic. So this is going to be random because this was random. So even if the planner doesn't inject any additional randomization, which it may do, but maybe it won't. But even if it doesn't do that, if the simulator was randomizing, then of course the outcome of all this computation is going to be random as well, right? And so for a given input S naught, this algorithm is going to produce a random output. And we can talk about what's the probability that this output takes a certain value. What's the probability that action 1 is the output? What's the probability that action 2 is the output? We can collect all these probabilities, right? So a planner like this is just an algorithmic description of what a policy is doing, right? In response to S naught, produce an action that is random action. What is that? That's the policy. So this planner implements this policy, which we could define as this. This is just like, okay, like S naught is governing this whole interaction because that's what the planner is reacting to. So that it uses this probability distribution together with the randomness coming from the simulator and the actions. And we can ask what's the probability that the outcome of this computation is a given action. You can collect all of this. And that gives you a memoryless stochastic policy. It's going to be memoryless only if the planner has the property that it doesn't cache anything. So no caching. No saving between calls, anything. If there is savings in between calls, then the planner is not really memoryless. It kind of learns about this word. But for a moment, let's just assume that there's no caching. So we have memoryless planner. Which is going to give rise to a memoryless policy as written above there. And then the exercise that we're going to get into today, that we want to do today, is to figure out whether we can write a program for a planner which would produce a policy, which is a good policy for the MDP, the underlying word. So the goal is that this policy that is being produced, this MDP, should be, near optimal. Maybe delta is the input to the planner. So here V star is the optimal value function. So we kind of demand that, okay, no matter what the input states are, if you use the planner in this closed loop system, right? Here, like going back to the first figure, there is this big outer loop, right? So if you keep calling the planner, it gives you these actions. So that means that you're executing this policy that the planner implements. And then you ask yourself, what would be the value that this policy generates if it is started, like the very initial state is S? Well, that's this value, V of pi of S. So you want to say that no matter how this whole thing starts, the value that our planner generates is close to optimal, at most delta away from optimal. Okay? This is what we want. Makes sense, right? What else would you want from a good planner? Okay? So this is one part of the goal. And the other part of the goal is that the amount of computation that the planner is doing should be controlled, right? Like, we would be doing this for nothing if the planner would still, like consider all the states and then do everything that we were doing previously, let's say with policy iteration. You want to save computation. So we want efficiency, which means controlling computation time. And we often also introduce another efficiency metric. I'll answer that soon. Which is the query, number of queries, the query cost of planning. So what is a query? A query was when the planner was sending a given SA pair to the simulator. Every such call is a query. Okay. So we had this question. I'm not sure I completely understood the question. Is the simulator just a sampling model or a full probability model? Well, the interface that we are assuming is that you can call this simulator with some state action pair, and it returns a next state and the immediate reward that corresponds to the state action pair, like executing the action in that state. Nothing less, nothing more. So based on this, I think that like this is not really a full probability model. Like it's not returning a probability vector. Returning the probability vector could be detrimental to us because there could be so many states that it would be impossible just to work through the probability vector. If you recall the lower bound proof that we were doing earlier, it was saying that planning for a policy that's good everywhere in the state space requires computation that scales quadratically with the number of states. One reason for that is because the next state distributions, as written with probability vectors, can have S components as its number of states. It's too large. A planner would need to go through that. That's too bad. We don't want that. So it's actually a big innovation, if you wish, to try to get away from this by using random outcomes. So it's like stochasticity. We are trying to leverage stochasticity to save on computation. And we also try to leverage on that we don't have to store actions for all the states because we can interleave computation with traveling in the world. So when you're in this loop, you have a current state that has some recency, that has some importance. You can do some computation. Well, you want to control the mode of computation that you're doing. So maybe you want to do some caching or something. Later on, we will see that that's pretty important. But you still want to focus your resources on computing what matters and do the computation just in time when it matters for the state that you just encountered. All right, so there was some other questions. All right, do we, okay, first, are you building the planner using interactions with the environment, or do you assume that it's given? I guess a related question is, do we also consider the accuracy of our simulator? Okay. So I think that these are the same questions. So the simulator is the same as the word? Well, there's no way, right? Like all of us feel that that's outrageous assumption. There is something like stability going on. So if you have a simulator that is closely enough reflecting key characteristics of the word, then planning with that simulator as if the simulator was the word, so satisfying this requirement. So in this requirement, there is no distinction between the word and the simulator. They are the same. So when I say, give me a good planner, I say, give me a good planner for this simulator, and I'm willing to assume that the simulator is the same as the word. With that requirement, give me a good planner. And then there is another result that maybe you will learn about, I'm sure that we will learn about, or you will do it as an exercise, because now you can do a lot of these things, that shows that if the deviation between the true word and the simulator in some sense is not big, then the plan that you return for the wrong model, the incorrect model, but not too incorrect, is not a bad plan overall for the original word. So there is stability. It's like this seem to real business. I mean, yeah, okay, there could be models, there could be examples where there is a slight deviation in the simulator, and then you are doomed. Don't go there. There is no other advice I can give you. Yeah, that like those are just like wicked problems, right? But you have to investigate this sensitivity question. So this is called sensitivity question, whether like how does it matter to what extent that the simulator is not the same as the word that you're being put in. But just investigate, and then you can separately investigate it and you know, separate these concerns. Like, I want a good planner, and that should be just like faithfully for this thing. And if the planner has no idea about how the word is different from like what, like this is the all information that it has, that like, okay, I have this simulator, the simulator doesn't say that, well, I'm not perfect here, I'm not perfect there, and this is the best that you can do. In a way, this is also called, like, this is an old idea, right? Just to, you know, build a model and then assume that the model is the word and then try to act as if the model was the word. This is called certainty equivalence in control. And Ben Recht really loves to talk about it. And it's a reasonable thing to try. Maybe later on we can talk about it, like when do you want to deviate from it and how, but under a large number of circumstances, it's just a good start. All right, so clarification question. If you call the simulator with the same state action pair twice, Do you get different return values correct? Yes. Every time, it's a fresh sample, independently of all the other samples that have been generated before. Yeah, okay. I already answered Sina's question. Okay. All right. Any other questions for this? The setup and the why and the what? All right. If not, then the last time I already explained a little bit about how we can do something about of coming up with planners whose query cost and computation cost is independent of the number of states in the environment. But today I want to revisit this, and I just want to say that, well, we already learned about value iteration, so why don't we start with that and just carefully think about what value iteration is doing and how we can use what we have already learned, and then I connect it back to what we've been talking about previously. So how does value iteration look like? So value iteration can be viewed as a planning algorithm. You start with, I don't know, some function over the state space. Maybe it's the all-zero function. And then the next function that you generate is just the BAM optimality operator applied to the previous function. So this goes on for k equals 0, 1, and so on and so forth. So effectively, what you have here is that v of k is the BAM operator applied k times to 0. And we know that this sequence of functions converges at the geometric rate to the optimal value function. We also happen to know that to calculate an optimal action at some state, so recall that we have this state S0, that's our input. And if you want to calculate an optimal action, all that you have to do is to do this one-step BAM on look ahead calculation, which takes the optimal value function and then says that, hey, what would happen if I tried action A? What would be the total value that I could generate that way? Well, it would be the immediate reward plus the discounted total future reward and the stochastic transition that is induced by my action at the state S0. But the future value is already summarized for me very conveniently by the optimal value function, because from the next time step, I'm acting optimal. I just want to figure out what to do now. Right? So this gives me the optimal action. So that's great. And well, we already see some problem that this inner product, this is just the expected value. Sorry, this inner product, the expected value of V star over an x-state distribution. If you would try to do that in exact form with vectors and whatnot, it would take forever, but maybe you can use sampling, right? So we know that if you have an IID sample, for example, then the sample mean of that sample converges not that fast, but like at a reasonable rate. This inverse root number of observations or number of samples rate converges to the true expected value. So you can imagine sampling from this distribution, m samples, m states, and then just take the average of v star at those states. That should be a good approximation. So you could try to do this, and then replace this expected value with just the sample mean. All right. But of course, v star is not known. Okay, someone disagrees. But still, v star is not known. We only have, let's say, v of k. So we can't really do this. So we are going to do something like this. So replace v star with v of k. And then maybe you can imagine that this is just like a crappy approximation to this next state distribution. So this, you can call this the p hat, and then you put a hat there, and then, okay. Now you have approximate computations. And well, the problem is that we still need to calculate v of k, right, at all these next states. Okay. And how much is that going to cost us? This is not that hard to figure out if the underlying word or MDP was deterministic. So in a deterministic MDP, when you're calculating this v of k at some state, this is t to the power of k applied at 0 at s, and they just, you know what this Bellman operator does, it just does max, and then does the one-step Bellman look ahead. I have to write it again. And it applies it to the value function that's obtained by applying the Bellman operator to the identically zero function, now just k minus 1 times. Right? If the system is deterministic, then this is a Dirac at delta of, I don't know, the next state is maybe GSA. So S prime with probability 1 is GSA. So that's the dynamics of the system. This is just a Dirac. So all this integral is doing is just plugging in. So it says, calculate me this value, this whole value function, every state. But I only need the value of this at the GSA, right? So this calculation is just this. You can see it's a recursive calculation. You say that, well, first, recursively, let's get a value at this state, GSA, for this given S and A. So my input is S to this function that wants to calculate Vk of S. Okay, so we know that this is V of k minus 1. And how do I calculate this? Well, I go through all the actions So there is going to be a for loop. And for each of the actions, so maybe I have this v function which calculates vks, right? So that's the purpose of this function. It's going to have a for loop. Inside a for loop, I guess it has to recursively call itself. And it's going to say that, well, okay, so we have access to this g function. So let's get this value. I need some array. Okay, like pseudocode is really difficult. You guys speak Python, right? I'm just going to say, all right, I'm going to do some calculation of a values. And the a values are going to take this form. All right. And then we see that, oh, Java is going to make a mistake if the base case is not handled properly. So when k is 0, then just return 0. This is the base case. If you're not in the base case bigger than 1, then just do this calculation when we are looking up the reward, adding, discounting, look up the value for k minus 1 at what state? Well, at GSA. And then do this for all actions. And then just return the max of q. That's beautiful. That's our first pseudocode in this class. All right. So you can just write this code. It's a recursive call. It's going to finish, right? Regardless of the size of the state space, this finishes. If I call it with a fixed k, it finishes. It's just going to do it because, you know, k goes back. Eventually it's done, then k equals 0, it returns. That's where the recursion finishes. So what's the total compute time that we are spending on this? Anyone wants to guess? Big O. Just elementary operations like addition, like, and I don't care about, you know, like little details, just like roughly, if I call this with k and there are a actions, what's the compute time? So where is the costly step?
The recursion is pretty expensive.
Yeah, the recursion is going to be quite expensive, right? Like here, this for loop for every action is going to do a recursion, right? Okay, so there are some guesses which seem to be correct. So yeah, like this is like an aphod branching, and then you're in a branch. In that branch, you're calling v, the same function. It does an aphod branching. It does it how many times? If I even initially call it with k, the depth is going to be k. So the total computation is the same as the number of nodes in this A array tree. So here A is equal to 3. A array regular tree that has a depth of k. And this is going to have roughly a to the power of k nodes. And so it's pretty expensive, but it's independent of the size of the state space. And that's like, wow. All right. We don't have to be slaves of how many states there are in the environment, in the MDP. If we can do local planning, and okay, for now we have a we have a deterministic system, no stochasticity, then we can get away with computation. Well, we don't know how to set k, but like, can you guess how k should be set? So what value of k should I use so that at the end, when I read out my action here, then I will get a good policy, roughly. I want delta suboptimal policies. How big should be the k? Or age, yes. Thank you, Kenneth. So age was what? It was the effective horizon, right? So k is going to be age. Gamma, I don't know, like, there are little details like here you have to multiply with 1 minus gamma squared, but like that doesn't matter. That goes into log. So it's basically 1 over 1 minus gamma and some log factors. Well, it's like, if you care about the log dependence on the data, then it's log 1 over data divided by 1 minus gamma, and there are some 1 over 1 minus gamma log factors that I'm ignoring. All right. So that's how big k has to be. And so the computation and the number of queries, so these are the queries now. And the other part of the query is getting the reward. Everything is under control. Okay, it can be a little bit large. If gamma is like 0.99, then this is a gigantic number. If gamma is 0.5, then it's kind of manageable for a small number of actions. So maybe this is not super practical yet, but already tells you that the computation in this model, if you change to this local planning model, doesn't need to scale with the number of states. Right? And that's very important. Right? We can put on additional speed ups and whatnot. Also, I already drew this little tree here. So you can see that this value function computation is really just these backups in a tree. Like you're building this look-ahead tree of a fixed depth. The branches correspond to the actions that are available to you. At the nodes, you're going to do this max at the end. So there's a max operation, and it's just like this value backups are happening in this look-ahead tree. Good old trees for search make an appearance. It's not super surprising. Dynamic programming is basically about this look-ahead computations, but you do it in many different ways and different ways of caching things. Okay. Big outstanding question. What happens if the system is stochastic? Right. So I already alluded to that maybe you can use sampling to help yourself with stochasticity. So you don't want to do this big averaging over S next states. Sampling can save you on that. So this gives us the idea that maybe we can push this a little bit further. And in this recursive computation, if you don't have a deterministic system, but you have a stochastic system, you could still do this in a recursive way, right? But just sampling just in time. Okay. So here in this pseudocode, you can imagine that instead of, if the system is not deterministic, you can just like say, give me the next state. Like that's unreliable. And you're gonna say, give me M next states. I'm gonna take the values there and then average over M. And I do the same backup. Okay. So this is the algorithm. Okay. And we want to claim that you don't have to introduce too many next states. The number of next states is that you need to sample. If it was a lot, if it would depend on the number of states in the MDP, that would be the end of the story. We wouldn't have a story. But it's only going to depend on the data, the desired suboptimality level, and the discount factor. And it's basically going to be, again, I think, the effective horizon or something like that. And then maybe some polynomial part of the effective horizon, like cube or something. And if you have that, then the computation time, if you have M samples for each state action pair here, the total computation time for all this is going to be what? Your branching, if you have a stochastic system, then the branching looks a little bit different. So, okay, let me, come on. So you start with a state, and then you have, I don't know, 2 actions. And then you would sample, I don't know, 10 next states. Okay, that's not 10, that's just 4, but I can't throw more. And then you would go in, oh, like these are the next states. Then let me get again the 2 actions going, and so on and so forth, right? So you interleave choices between the actions, and then sampling next states, and then keep going. If you pull together these 2, then the branching between layers of the put together layers is M times A. If you have M next samples, so the green guy, the number of green guys is M, the branching is M there. The branching with the purple or red guys is A. Then altogether the branching factor is MA. And the computation changes to from here to MA to the power of K, right? Because that's how many nodes you're going to end up at. All right. Any questions? Okay. So what remains is to figure out how to set M. Because we don't quite know how big M should be. Maybe it cannot be chosen as a polynomial function of the quantities of interest. So to do the analysis, it will be useful for me to slightly change things a little bit. So I was sweeping something under the rug, a minor thing. The minor thing was that where first you do the calculation of the value function at these states, and for a given action in S naught. And after you do that, you would do this calculation. It's kind of the same calculation as would be done here in the main routine. So the calculation here would be basically the same. I mean, like it's one step down, one look ahead. And you do this for all the actions, and then you choose the max. And there is an uneasy feeling about that, like, why are we treating the very first step of this process differently than the rest? Well, it's because we are focusing on these what's called state value functions. So if we introduce what's called action value functions, then all this becomes much nicer, more homogeneous, and easier to write the proofs. So that's what I'm going to do next. So to address this issue, slight inefficiency in arguments and asymmetry that is unwarranted, that somehow the very first step is different than the others. No, it shouldn't be. So the calculation that we were it suggested to do, we figured we should do like this, right? And if we knew the optimal value function, that this is what we would do. And this value here, okay, let me just do it for general S. So this value here is given a name. It's the optimal action value of action A. Optimal value of A. The meaning of that is that if you choose action A and then you continue optimally the process, this is the total value that you would get. You've probably seen this zillions of times. And we know that the Bellman equation actually tells us, by the fundamental theorem, that V star is the max, just the max of this, right, over the action. So it's equal to the maximum of Q star at SA over the actions, right, for every state. That just follows from the Bellman optimality equation. And we also know that V star of S satisfies the Bellman optimality equation. So, I mean, okay, so if we, sorry, I will repeat the definition of just Q star SA. So this is just equal to RAS plus gamma times the look-ahead value of V star. But like, instead of V star, I just want to write Q star here, but I can't really write Q star. I need to write the max over A prime Q star at this unknown state that we're going to arrive at after one step of transition, and then take this maximum. And if we introduce this operator M, which takes functions over state action pairs and returns functions over states, which just takes this Q function and returns this function MQ, which at state S is equal to the maximum of Q as A over the actions A. Then with that, this whole business, which just followed from the definition of Q star, and then the observation that from the Bellman optimality equation, V star at any state is equal to the maximum of Q star over the actions at that state. So then we can write that Q star SA is RAS plus gamma PAS, and the M operator, this maximization over the actions operator applied to Q star. And this becomes a fixed point equation in Q star. But the nonlinearity is hidden here. So that's the max. So this is the Bellman optimality equation for Q star. And we also like to introduce all these operators, and you see that in the exercise, and then you can just write that, I don't know, Q star is equal to R plus gamma P M Q star, where M is already defined, the P operator, that's just like the transition kernel operator that takes value functions and returns state, that takes functions over the state space and returns functions over the state action space. And in particular, if its input is V, then the function that it returns is, so P V at SA is just going to be, as expected, the average of V over the next state distribution induced by taking action A at state S. And finally, this R object that's unnamed here is just seeing the reward as a function in SA, space SA. Just renaming. And well, if you want to be even more fancy, then we can introduce this operator which assigns to a Q function the value of R plus gamma P M Q. All right. And then it follows that Q star is the fixed point of this operator, right? Because that's what we started with, like that. That's just this written in operator form so that everything is more compact. Okay. Also, from the context, it's clear that this operator applies to action value functions, then the tilde can be dropped, and it is often dropped. So if I write Q star equals TQ star, it would be a syntax error if I try to apply the Bellman operator that applies to value functions on Q star functions. They are not compatible. So like a good programming language is sensitive to what the parameter types are. My notation is also parameter type sensitive now, right? So this T operator from the context is understood to be this operator here. And so there is a question whether there's an equivalent action value operator to T of pi, in the sense that t is sort of like the action value equivalent to t? Absolutely, yeah. You just have to. So what would that be? So the only difference is that you take this m and you replace it with m of pi, where m of pi is not taking maximum over the actions, but takes average over the actions with respect to the distribution over the actions induced defined by this memoryless policy pi. And that's a linear operator, so the underlying t of pi or t tilde of pi would also be a linear operator. It's like everything is kind of the same. Okay. All right, so what's the big fuss? So why do we do this? We do this because now we can just write the algorithm with one line. Okay, so the value iteration algorithm for the deterministic case is just this, argmax. It's always nice to write something with just like one formula. T applied k times to the zero function, and then you have this S naught, and this is your algorithm. Okay, this is it. This was the previous algorithm. There is no like separate look ahead and like do the VK calculation, do this, do that. No, nothing. It's just like do this k times. Recursive call, deterministic systems, easy peasy. Everything is the same otherwise. Okay. So what happens if you have a stochastic system? You can approach this in two ways. So one was that you look at the code here, the pseudocode that we had, and then you would, like here. It's so bad that I don't have a pointer here. So you have this, and then you would need to generate the next states, m times average, and every time this happens, this call happens, you would just call the simulator, get those next states. All right, so that's one possibility. The other possibility is to think like, I don't know, as a mathematician maybe, I don't know, but just think about that. Well, maybe we want to approximate this t operator. So we want to replace the t operator. We don't like the t operator because it's like too much computation to compute it. We don't like it. So we want to replace it. So what was this t? So the t was doing this calculation. So which part of this we don't like? Which part is that we don't like? Which part is it costly? The inner product, yay. Too costly. So replace this with just like this p head of as or something, which would be this Dirac's placed at this next states. So the PAS replaced with this empirical distribution induced by samples generated from the simulator, calling the simulator m times. It gives you next states. And then you just want to average. Every time you need to use this operator at that state, like you just use that sample. So you could write this by saying that, okay, let's collect this sample once for all. So, this is going to be a list, right? So you have for this SA pair m next states. So this is sampled from this distribution for I going from 1 to m. And these are independent. Everything is independent of everything else because the simulator always gives you fresh samples. So you collect this list for a given state action pair. Imagine you're doing this up front. And then you introduce this operator, which is the t hat operator, which is going to do the same calculation almost, except that the inner product is going to be replaced with this very convenient average. So you take the S prime, which goes through the elements of this list, and then we plug in into MQ. Okay, that's too fancy. So we can expand that. So they're just like max A prime and Q at S prime A. Okay. All right, so this is our approximation to T. So we're gonna hope that this is the same, like close or something. And if they are closed, then maybe their fixed points are closed. And maybe if you do the calculation with t hat, it's not a big deal. Right? So first of all, what is the algorithm? I love it when you can write an algorithm with a one line. So this is the algorithm. So now everything is defined. Just take this t hat, raise it to the power of k, and get the values, take the max over the actions. Boom, done. Okay, does it make sense? It's like a random approximation, right? If you want to use big words to this operator. So, okay, so what's the complexity of this? Did anything change? Well, we can do it recursively, right? Like we just have to expand this recursively. We do the recursive calculation. The branching factor now is a little bit different, right? So before we were branching with, right? Like this is the recursive calculation that you need to do here. Like this will be the call. How many times do we need to do this? Well, for a given state action pair, you have to do it for all the next states. And here you have to do it for all the actions. So the branching factor is going to be m times a, right? Because we have a sum and we have a max. The sum is over m possible values. The max is over a possible values. So the branching is m times a. And the depth is going to be k. So altogether, all right. Let's next line. So since the branching factor is ma, the depth is k. The calculation, query complexity. So this is the cost. Query cost is bounded by big O ma to the power of k. Good. Okay, question. Are we going to gather fresh samples every time we apply Tito? No. Well, I propose not. You can cache those values. So imagine that you're doing this recursive course and do memorization. So use memorization to get the CSA list. Okay. So just like have some global structure where you're storing whatever you already computed. That reduces the query complexity, and it can reduce it quite significantly. If your simulator is expensive, you definitely want to do this. You may worry about that. This is going to introduce some problems. Happens, it doesn't. Yeah, you need to memorize. No, the CSA doesn't depend on the depth. So when you do memorization, you might think that you need to memorize on all possible, like the inputs are the depths, the state, and the action. And you would, so that was the question, whether you need to do memorization on that. Well, for CSA, you can just like decide to share. That's fine. You could also decide not to share. And every time you need this list, you would regenerate it. That's a different algorithm. I'm talking about the one that caches, that saves things. They are by and large the same, and the analysis is not that much different. So it's like it doesn't matter, right? My doggy doesn't like the action on the road. Okay, yeah, that's interesting. All right. All right. Okay, I think that I did answer all the other questions. Maybe I need to do something with the doggy, so hang on for a second. All right. So I guess you had a little break. You had some time to think. Are there any more questions? No? Yes?
Does memorization affect the IID assumption?
I mean, like, you make this assumption. I mean, you just ask these samples from the simulator. They are fresh samples, but you only do it once for every state action pair. So what do you mean? For a given state action pair, the sample is going to be IID. The next time you reuse it, of course, maybe there is some correlation already, so maybe you should worry about that. So in that sense, yeah, like you got to be careful, but it turns out that it doesn't matter. So these correlations are so mild that they cannot destroy the process, which is really fast converging. Okay. All right, so how do we analyze this? Okay. So we kind of hope that, okay, we're going to use some effective horizon age or something, apply it to 0, and then that it will be close to Q star. But we can't hope that this is going to be true everywhere. It's not, right? Okay, so only true and only needed at S naught, right? So we don't need to approximate Q star well everywhere. We only need to approximate it well at S naught. And the process, it's not doing too much calculation, right? So it just like builds this tree and like does this calculation. Everything is focused around S naught, right? So on the top of the tree, you have S naught sitting there. There are all these actions below it and so on and so forth. So here you have high precision. And with an increasing depth, you expect low precision. So if a state occurs in this recursive process very late, you don't expect a high precision there at that state for t to the power of h naught, because you only apply these things at S naught, right? So all the computation is focused at S naught. So if you want to understand how precise we're going to be, we have to be careful in how we analyze this. So we can't expect high precision far from the state, far from the initial state. So you're gonna collect, into these various sets, the states that are at various distance away from the initial state. So you can think about that, okay, here's S naught, and then this CSA, so this generates all the neighbors for all the actions. So these are the immediate neighbors as F S naught. And then there are the neighbors of those, and then the neighbors of those, and then sometimes this goes back. Okay, and all this is directed. So there is this directed graph. And in this directed graph, you can calculate how far the state is from S naught. So basically, you put into SH all the little states in the state space, which are in this graph at a distance less than h from S naught. So S of h is going to be all the states that are encountered. And then, so as I said, we want we want to argue that the accuracy is going to be great. Okay, this is t hat. T hat of h naught s naught a minus q star s naught a. This is what we want to argue about. And you can imagine that we want to recursively expand this difference. And if we do so, then we're going to encounter states at increasing distances from S naught. So here you have the S naught states, like that, just S naught, and then here S1, and so on and so forth, S of h. And so this suggests that maybe we should introduce these accuracy metrics, which are T of h applied to 0 minus Q star, the difference between these guys, but only measured in the max norm over the subset of the state space where we expect the accuracy to be high. So initially, so let this norm. So if you have a Q function and I put some S subset of the state space there, then this is going to be defined as the maximum over S in S and actions or possible actions of Q of SA. So this is the restriction, this is the max norm of the function restricted to this part of the state space. So we expect this guy to be small, and we expect that this is going to rely on how small this other guy is, which has one less application of the approximate Bellman operator to 0. And we measure the deviation to Q star. On the next one, a little bit bigger subset of the states. So this part of the states here. So S1 up to any delta h is going to be defined as t hat applied h times to 0, deviation from Q star, and take the max norm over the states that are within a distance of h, capital H minus little h. So if you go like this, then you get delta naught, which is t hat 0 times applied to 0 minus Q star applied to S of h. And, well, this is nothing, just 0, not applying t any number of times. So this is, of course, smaller than equal to than 1 over 1 minus gamma, which is the size of Q star. And now we can try to relate these guys. So delta h plus 1 is what? It's t hat to the power of h plus 1 applied to 0 minus Q star. And the norm should be I don't know. Okay, let's do it with h, because I already have that. I don't have to think. So if h is bigger than 0, then because h equals 0 is handled here. So that's kind of the base case. And now we will try to build the recursion. So now we have this deviation, that's the definition, and we are going to add and subtract and use the triangle inequality. And what are we going to subtract? We're going to subtract t hat applied to q star. So we have to add it back too. And in this second term, I'm going to also change the norm to increase this set to the maximum set. So remember that S of H is like includes all the states that were ever encountered in this computation. And so here we'll need to bound this term in some way. And well, let's deal with the other one. So to deal with the other one, so since H is bigger than 1, we can pull out the t hat, and we get t hat applied to t hat H minus 1, 0, minus t hat applied to q star, plus this other term. Okay. I guess I would just like copy this here. So we want to bound this. And so this is equal to t hat applied to t hat H minus 1, 0, minus t hat applied to q star. And so there is this function, and there is this other function, and we apply t hat to both of them. Guess what? T hat is a gamma contraction, right? But t hat has the same structure as a t function. It's like r plus gamma p blah blah blah. So it's a gamma contraction. So this is smaller than equal to gamma times t hat minus 1, 0. Okay. I have to be careful here. All right. So call this function, I don't know, you call this function v. I have to be careful because the maximum is taken over this set. And the question is whether when I'm comparing u and v, I want to take the set to be 1, which is 1 bigger. And whether I mean, okay, let's see how this works. So t hat applied to u is what? That S is RAS plus gamma P. No, not that one. It's like here comes the average, the new part. Right. And let u prime be mu and v prime be mv, okay? And so we have to take the value of u prime at s prime. So here, we're taking all the states that are at a distance. So this state s is such that its distance to s naught is smaller than h minus h. How about this? Well, it's a child of this state, so its distance cannot be more than the distance of s plus 1. So for all s prime children of the state s under any of the actions, distance cannot grow by more than 1. So its distance is at most h minus h plus 1. So the s prime is surely within that set. So you can apply t hat, of course, to v as well. You get a similar calculation. Then you take the difference between the two, the rewards cancel, gamma comes out, and you will get that this is smaller than equal to gamma, oops, over m of the maximum over all the states in sh minus h. And here, well, all those states don't matter. So I can take all the s primes in h minus h plus 1. And yeah, just write it here. U prime, S prime, minus, okay. All the S primes in CSA, okay. All right, this is not good. And take the maximum over the AS one. Okay, let me fix this. Trying to do too much in too little time. So this is less than equal to at a given SA pair, but then I have to take the maximum of all S in here, all the actions A, these guys cancel. There is gamma over M, and then the sum over all the children of SA, U prime, S prime, minus V prime, S prime. Okay, so now you can bring in the absolute value inside. Use that an average is upper bounded by the maximum value. So this whole thing is upper bounded by gamma times the maximum over S prime. And you also that if S is in here, then S prime is at the distance of H minus capital H minus small h plus 1. So can just write this set here. And so you get this, which is smaller than equal to U minus V norm taken over H minus H plus 1. Okay, and now look at what U and V were. So because of the definition of U and V, this is just delta of H minus 1, right? So we see that this first term here is going to be bounded by gamma times delta of H minus 1. And if we think that, okay, somehow we will be controlling this term, so it will be small, then we get this recursion going on that delta H is smaller than equal to gamma times delta H minus 1 plus small value times or divided by 1 minus gamma. And then you can calculate that delta H is going to be small. Okay, we are going to do that next time because it's getting way over time. And so outstanding, what is epsilon prime? How does it work? And then finish this calculation. And then finally, we will need to argue that we can set the value of M and H as a function of the desired accuracy or suboptimality level. And then the question is how big are these? Okay. Okay, I can answer some of the questions in the chat. So I think that this question is jumping a little bit ahead. Fengdi is asking that to bound the error of P minus P hat MQ star, do we prove martingale, bound variance, and then Bayesian inequality or any simpler way? We're just going to use Hovding's inequality for bounding this. And we're going to be careful. So this is controlling the epsilon prime term. So for the epsilon prime term, what's really nice about it is that the random error of the t-hat operator only ever comes up when it's applied to Q star. It's beautiful. It's like you don't care about how well t-hat approximates the effect of t at any other point, only at Q star. If you want to do a good job at approximating t, this analysis shows that all you have to do is to approximate it well with Q star, because you can always do this subtract and add Q star business. And you don't have to worry about how t hat behaves at any other function. And now, since Q star is a fixed function, like it's not hard to see that at a fixed function, the sample averages versus these expected values that are close to each other. In this whole process, the total number of states that you can ever generate is bounded. So you take a union bound, you use Hovding's inequality, and you're good. The union bound is very nice because although there are many, many states here, ma to the power of h states, if you take the log of that, they're just linear in age. It's nothing. And then m has to compete with that, and then that's why m is going to be roughly of the order of h, which is the effective planning horizon. And so there is a bigger lesson here, and that's also why I wanted to present this proof this way, which is that you can take this operator view and apply it to designing all kind of algorithms and analyzing them. We can write them in one line, and in the analysis you will see that what only ever matters is like how the operator behaves at this unknown function Q star. So you might wonder about, okay, what's the big deal? Well, you may have some guesses about how Q star behaves, and like maybe you want to adjust your things to that. So you could have some extra feedback loop that tries to exploit that. So yeah, and the analysis is not super complicated. I mean, it's just like a bunch of triangle inequalities, contraction argument, done a little bit carefully, and then this is just a Hoeffding's inequality. All right. There was some other question about initializing V naught. Some other way. So I guess maybe the question is, why do we initialize at 0? I think 0 is just convenient, and I don't see any way of generally without extra knowledge improving this. But what I said at the beginning when we talked about value iteration still applies. So if you had some guess about what Q star is, just initialize your value function to what Q star is. Initializing high or anything like that doesn't matter here. Like if you're not trying to be optimistic here or doing any fancy stuff like that, we just want rapid calculation. And then one related question is, like, there are lots of questions like, could we stop this early? Could you do some pruning? Can you notice that in some branches the calculations are superfluous, right? So you want to save on computation, then you could try to come up with lots of tricks that people did, and there are much fancier versions of this process. But we're going to talk about this later. Okay. Anything else?